Good morning, everybody. Today we have another Codeforces round. This one's round 742. We have a slight camera adjustment upgrade. Who knows? Maybe it's better, maybe it's worse. I guess we can always go back. So there's that. And then also, I've got a new graphics card. Or not graphics card, like graphics converter thing. So if this freezes, I have no idea what's causing it. I'm going to lose it. But if it doesn't, then there we go. I think I may have fixed that problem. So here we go. Let's jump into the contest. Solutions to this contest will be at the end of the video if you're looking for those, and I'll have a timestamp to when they start in the description. Otherwise, let's jump into it. All right, domino disaster. Alice has a grid with 2 rows and n columns. She fully covers the grid using n dominoes of size 1 by n. Alice may place them vertically or horizontally, and each cell should be covered by exactly 1 domino. Now she decided to show 1 row of the grid to Bob. Help Bob figure out what the other row of the grid should look like. So left, right, D is what? Down and up, I guess. So replace all of the L's, or keep out the L's and R's, replace the D's with U's is the problem, I guess. All right, cool. Yeah, that's pretty easy. We can do that for sure. Yeah, I don't even need to explain it, I think it's just pretty self-explanatory here. So replace all D's with U's and print the line. We should be good there. Oh, am I not registered again? Man, this is like the 3rd contest in a row. All right, here we go. So D. Oh. All right, cool. Well, we should be good there. Oh, I am registered. No, I'm not. Okay. Yeah. So that's problem A. We'll move on from that in a minute. For problem B, Alice gave Bob 2 integers, A and B, and Bob wrote down an array of non-negative integers with the max of all elements equal to A, XOR the value of all elements equal to B. So the max is A and the XOR is B. Okay, what is the shortest possible length of the array Bob wrote? So it's either A minus 1 or A. Yeah, so we have several test cases, but it's always a prefix. So this should be pretty easy, so we can just say, let's just do it here. Do it as we type. So we'll say int array XOR prefix. So new int array, we'll make this size 10 to the 6th. And we'll say for int I equals 0 less than XOR prefix dot length I plus plus. And then XOR, I guess let's start this at 1. XOR prefix at I equals XOR prefix at I minus 1, XOR I. So this will get us the prefix of for any numbers. It'll give us the prefix of it and all numbers less than it. And then we can answer the test cases really quick. So we'll have int A equals this, and then B equals this. And then yeah, so if XOR prefix at A minus 1 is equal to B, then the answer is A minus 1. Otherwise, the answer is A. And we should be good there. So, oh, no, why not? So we need the max equal to 1. Oh, yeah, okay. So I guess, yeah. All right, so there's one, yeah, we can't make the max too big. So, okay, so otherwise, what's needed would be XOR prefix at a minus 1, so this is what we have, XORed with B, which is what we want. So if needed equals 0, then we have to have this case. Otherwise, if needed is equal to A, then we have to use 2 numbers. So in this case, this out A plus 1. Let's print A. We're wrong in the second case now. The XOR of 2, or the max is 2, the XOR is 1. 0, 1. Oh, these need to be plus 1? Yeah. Was A plus 2, I guess? Yeah. I think that should be good. I wonder if they test this anywhere. 0, 1, 2. What if we comment out this line? Is this getting hit in samples? It is in the first case. Okay. Good. All right. Cool. Cool. So let's move on to problem C, I guess then. Alice has just learned addition. Well, good for her, right? However, she hasn't learned the concept of carrying fully. Instead, she carries to the next column. Oh, instead of carrying to the next column, she carries to the column 2 columns to the left. Okay, I see. So the regular way would be to do this, but she offsets everything by 1. Or by, yeah, okay. All right, she gets the incorrect result. Alice comes to Bob and says that she has added 2 numbers to get a result of n. However, Bob knows that Alice adds in her own way. Help Bob find the number of ordered pairs of integers, such that when Alice adds them, she will get the result of n. All right, how many pairs are there? Or how big is input? So 10 to the 9 is the sum. And we have 1,000 test cases. Carrying conundrum. Problem C. What a name. Do all of these have great names that I've just missed? Okay, we got some alliteration. Domino disaster. Mex or mix-up. Carrying conundrum. Interesting. I'm interested. What are these? Oh man, this could have been problem E. Expression evaluation error. Okay, there's some good thought that went into this. I like it. At least into the problem naming. It's good, good. Okay, so yeah, so we have some result, and we want to know how many pairs of integers could hit this result. Well, okay. Suppose we know, let's say we're adding some numbers here. Hello? Okay. So let's say we're adding some numbers potentially, maybe like this number and this number. Our potential carry bits are this, 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 and this. But we can't ever carry in these last two positions. So in this case we have 4 positions, but maximally we would have 9 positions here, or maybe 10. I guess let's just say 10 to be safe. So if we suppose we know which of these spaces get carried, which of these have a 1, we know which column it came from. So we know if there's a 1 here, we know it came from this column. And then we know what the solution here is. We know this adds up to maybe 16. And then we know whether there's an input bit here. So maybe this is a bad example. Maybe a better example would be this. So maybe we know this is a 1. We know this is the input column here. And since we're brute forcing all of this at once, we also know whether this is a 1. Let's say it's a 0 here. So we have a 0, and then we have these 2 numbers which we don't know. And then maybe we know they add up to, this is a 6 and this is a 1, so they add up to 16. So we want to see what pairs of numbers add up to 16, and then also it doesn't matter what these pairs are as long as they add up to 16, because everything else is the same from our perspective. So yeah, so it's just like how many ways are there to pick 2 numbers that add up to 16. And that should be good. You can't add up to 20 ever. So I think we should be fine. Yeah, so brute force what this mask is. And then see if it works. Alright, cool. When can we register? We can register. Awesome. We should have A and B. We got wrong answer test 1. Wrong answer test 1 for real. I guess I never actually ran samples. Oh. Oops. Place all ups with downs. Okay. Looks good. Awesome. Pretty sure we got A right. So let's move on to C real quick here. So, yeah, what are we doing for C? No, we didn't. We got A right. Don't be silly, Codeforces. Down, left, right, left, right. Oh, okay. So I guess down and up don't matter, really? Oh, because you can give us either the top row or the bottom row. Yeah. Okay. There we go. So we got A. Alright, so back to C. So we have this test case. This is multi-test case, probably. Yep. and then we're given the sum. So we can read this as an integer. Although maybe we shouldn't. Yeah, it might be smarter to read it as just a string. So we have this, and then we probably want this is new int array size 11. Yeah. Or maybe 12 even. Okay. Then for int I equals 0 less than 12 plus. Okay, so we'll have this end bits is like the ending answer for us. They're not really bits, I guess they're digits, but I think it's still helpful to have them stored from like least significant to most significant. And then what else do we want? So then we want to brute force the mask. So we'll say for int end mask goes from 0 to 2 to the 12th, I guess. We also probably want the number of ways to reach sum total. So we have the number of ways to get all of the numbers 0 through 20. We really only need 0 through 18 probably, but that should be fine. Maybe 0 through 19. Okay, so then we know the end mask. So if end mask and 3 is not equal to 0, then continue. This is a bit silly because we might as well just only go to 2 to the 10, but this works. And then we want to see how many ways are there for us to do it. Voice crack. So then, okay, so yeah, let's brute force the position. End position. So then, yeah, just like, so first we want to like check if this is even potentially legal. And then next we want to count the number of ways. We should probably do these together. So int n ways initially is 1. We just do them together. And then, yeah, this will be 0, and then print the answer at the end. It won't be bigger than n, I think. So we should be fine. Then we'll print the answer at the end. Okay. So here we'll say ans plus equals ways. In ways, I guess. So then we have this ending position. So yeah. So if end position is, well, we don't even need that. We just need int min sum would be so like, I guess what is illegal here? Only if, it's only a problem if we have a 1. A 1 carry bit, and then a 0 sum bit. So yeah, because otherwise we should be fine. It's just you can't ever, 2 numbers never reach 19, so that would be the issue. I guess in that case, n ways to get 19 would just be what we're looking for. Yeah. Okay, so let's just say if n bits at end position equals 0 and end mask and 1 left shift end position is not equal to 0, then n ways equals 0, and then break, I guess. So otherwise we don't necessarily have that problem. So for this end position, we want the target sum. If this is the case, then we want end bits at end position -1. Otherwise, we want end bits at end position. Yeah. So subtract 1 if we need. And then we just need to pick numbers that add up to this. Is that the case? So we should make whatever this answer is a long. It's probably also safe to make this a long. And then I think we should be fine. Is it -1? 48. Oh, this -0. Good morning. There's a dog outside. Anyway. Hello. Okay, okay. It's a very active dog. Very active dog. We'll let the dog have its fun and then continue after. So what are we doing here? Okay. They give us examples. So in the first case, oh, I see. Do the two numbers both have to be positive? Positive integers, okay. And they're ordered as well. I think I should be counting whether they're ordered or not. I am counting that. There are also 2 more ways of doing it, right? So it should be answer like -2. Cool, so this out. So let's look at just this first case. For nmask 0, got 2. Okay, so those are the two ways we subtract. For nmask 4, got 3. So that's not right. I guess what is the target sum? So the target sum should be we might need to add. Okay, so if end position is less than 10 and the end position is less than 10 and we have this bit on at our position plus 2. Then in this case we need to say target sum plus equals 10. And then here we really just want to check if target sum is less than 0. Okay, that looks right. 9, 4, 7, 44, 99. Sounds good. Okay. And then how many test cases? Only 1,000, so we should be fine. Looks good. Nice, nice. All right, on to problem D then. On the board, Bob wrote n positive integers in base 10 with a sum s. Okay, in decimal numeral system. Okay. Alice sees the board but accidentally interprets the numbers on the board as base 11. You see, this is a very common mistake. You know, I do it all the time. I'll see a number and I'll be like, wait, this is base 10. That must mean that's 11 because 10 in base 11 is of course 11. So Bob is writing these in base 11 and Alice is reading them in base 12. Okay, anyway. Yes. What numbers should Bob write on the board so that Alice's sum is as large as possible? What? Oh, the sum of the numbers in base 10 is s. But when you convert these numbers to base 11, what do you get? SC. Well, they're all positive. It's kind of annoying. Their multiple answers print any. Interesting. So equivalently good, I think. Oh wait, no. That is the only good way of doing 100. Yeah, so you've got some number, I guess, and you want to split it up into different factors. So you've got some number, man, so many notes. So you've got some number like this. Well, you've got some number. Let's do a decent example. I guess 111 might not be terrible. So you have some number. You want to split it up into parts so that each part has, like, this first digit you get no bonus on. So this is just like the default. So like, I guess, yeah, you get plus 0 here. So let's say you write down A, B, and C. So from this, you get A times 121 plus B times 11 plus C. So you want like as much as possible to be here. I guess this is really, so like this is minus 100 because you pay 100 things for it, and this is minus 10. So you get like 21 times A plus 10 times B plus C. It's kind of annoying, isn't it? Yeah, that's not really fun to solve, I guess. Let's read problem E, see what's going on there. Non-decreasing dilemma. Alice has recently received an array. Are we still in? There we go, look at this. It hasn't totally stopped yet. It's not bad, not bad. Alice has recently received an array for her birthday. She's very proud of her array. And when she shows her friend Bob the array, he was very happy with the present too. However, soon Bob became curious, as any sane friend would do. And as any sane friend would do, asked Alice to perform Q queries of Q operations of 2 types on her array. Update this element to Y, or calculate how many non-decreasing subarrays exist within the subarray of this thing. So count the number of contiguous ranges that are sorted. Oh, this is fun. Okay, so we have some array of a bunch of elements, and then we want to count how many subarrays are sorted. Yeah, that's a good problem. How do you do it? Well, all that matters is the decreases, right? Like, we have some elements. Anytime you have a decrease, what that means is that that splits the array in half. If you include anything in the left half, you can't include anything in the right because you'll go down. So yeah, and then when you update some value, you essentially have, you might create a decrease here. You might remove a decrease here. You might create a decrease here, and you might remove a decrease here. So we need some sort of segment tree maybe, which supports create, split, remove split, and then range sum, where this is like the sum of some other stuff. So this is very similar to the problems niches, I think, on the tree set. And we should be fine there. Yeah, we just need to check for each range. We're interested in the maximum, the maximum uncut prefix, the maximum uncut suffix, and then the sum of like squares of lengths across the entire array. each of which are buildable from only those 3 pieces of information. And then we don't need any lazy propagation. Yeah. So we should be good there. All right, E is very straightforward at least. So we shouldn't have any issues coding it. Well, I say that. We have no issues coming up with the idea for it. So let's just make the segment tree real quick. So we have these two. If they're different, we need the mid. And then we say L child equals new seg tree from L to mid. And then R child, the same thing, from mid plus 1 to R. So how are we going to structure this? I think it makes sense to say we have all of these positions, and then we have potential split points between them. So then some segment tree node would cover like these things. From there to there. I guess that makes sense. Maybe, yeah, maybe that's helpful. So you either have like 0 or 1. Yeah, so we'll just say a split point goes to the thing before it. Okay. So what does data need? So I guess we need int left uninterrupted. Left, I guess left straight. We'll call right straight, and then middle sum. I guess this needs to be a long, huh? And then this middle sum should also be a long. Here we want to return middle sum plus left straight times long of left straight plus right straight times long of right straight. So this is, we need to include the sides here if this is like the last time this is being used, like in the main method. We need to return like what is the actual value of this data, because these won't be contributed toward the middle sum, which may make it easier, I think. Okay, so yeah, so in this case, we should just return, okay? Yeah, I think this should be fine. We'll handle this later. So we need to finish this in a minute. We don't have any propagation, so that should be easy. I guess we'll just recalc at the end here. And then what else? We just need point update and range query. So void point update. We need the int position, and then boolean is cut point. And then we need a data range query int L to int R. So after this, we want to recalc. But here we want to say if leftmost equals rightmost, and we want to handle it. And then return. Yeah, that's fine. So if this isn't the case, we need to delegate this to one of our children. So if position is less than or equal to lchild dot rightmost, then lchild dot point update. Otherwise, our child dot point update. Okay, and then range query we'll handle in a minute. Okay, so how do we handle this? So okay, so if this is the case, then we need to calculate our entire data from scratch. So in this case, ants equals, let's just call this data actually. So in this case, data equals new data. So the left straight will be, left straight will be 1. Oh, this isn't entirely true. So I guess we probably also want the size, huh? Yeah. Okay, so we have the size as well. So we have the leftmost and the rightmost. So yes, if this is the case, then we want a new data. That's the size of the left. The size of the right will be, oh, this also isn't right. So if size is equal to left straight, then return just this. The entire thing is all continuous. Just return it. Okay, so we should be fine there. We're missing this. So the right straight size would be equal to his cut point. If it is, return 0, otherwise return 1. Size is 1. And then the middle sum is 0. Okay. Otherwise, we update one of our kids, and then we recalc. So this is point update done. Good. So recalc is going to be tricky. What about in this case? So, well, this is going to be very similar. The left is going to be 1. The right is also going to be 1. It's going to be 1 big, and then sum is 0. Okay. So range query. So, okay, so I think we should be basically fine here. We just need some way of combining these two. So static data combine, data L, and then data R. Yeah, so in this case, we just want data equals lchild.data combined with rchild.data. And then we should be fine there. And then for range query, it's going to be pretty similar. So if L is greater than rightmost, or R is less than leftmost, then just return null. Otherwise, if L is less than leftmost, or less than or equal to, and r is greater than or equal to rightmost, then just return data. Otherwise, we need to go to our kids. So data lants equals lchild dot range query, and then we need the same thing for the right kid. And then we're going to return combine of lants and rants. Should be that easy. Okay, so we have everything figured out except for this. How do you combine two things? So the size is easy. The new size will be simply l.size plus r.size. Okay, the new middle sum. Well, this might be a bit more tricky, so we'll come back to that, I guess. Let's think about the left straight. So if L dot uninterrupted, then I guess this is int new L. So in this case, we also have this. We also have like long new middle, and then int new R. So if the left is uninterrupted, then in this case, new M equals R dot middle sum, and then new L equals L dot size plus R dot left straight. Yeah, okay. So we have the new L. Yes, let's just make this equal -1. Make this equal -1 too, because we don't know. So yeah, if the leftmost is uninterrupted, we know for sure. Otherwise, new L is equal to L dot left straight. We don't necessarily know about the new M yet. So if R dot uninterrupted, this has no breaks. Then we want to say new R equals R dot size plus L dot R right straight. Yeah. And then new M equals L dot middle sum. New L, new R. Okay, otherwise this is just new R equals R dot right straight. Okay. So the only case left is if new M is equal to -1. That's the only thing we may not have set yet. Then in this case, then we want new M equals R dot left, or R dot middle sum. I guess L dot middle sum plus R dot middle sum plus this new thing, plus this bonus. So the bonus is where the two combined. So this would be L dot right straight plus R dot left straight times the long of the same thing. Yep, and then we should be good. So now we return new data of everything we need, which is new L, new R, new size, and then new M. Okay, and then I think we're good. Awesome. we have our array. We go through each query. We have the type. If it's type 1, we do one thing, otherwise we do something else. What if it's type 1? Then what do we do? So this is point update. We need a seg tree st equals new st from 0 to n-1. I guess 0 to n, yeah, n-1. And 4 into I equals 0, I is less than n-1, I plus plus. If a at I is greater than a at I plus 1, then st.pointUpdate, position I true. Yeah, okay. So we update this position, and then we should be fine. So then we just need to say, this is a point update, int position equals this minus 1, and then val equals this. So a at position equals value. Okay, so now there are two ways this might be an inversion. So if position is not equal to 0, then st.pointUpdate. So position I minus 1. And then, or this is position minus 1. And then whether it's a cut point. So it would be a cut point if a at position is greater than a at position minus 1. We do this if position is not equal to 0, and then if position is not equal to n-1, we do something similar. In this case, we update position, and it's an inversion if position plus 1 is bigger than position in the array. So that should be our point update, and then we need range sum. So int L equals this, I equals this. Both these need to subtract 1. And then int ans will be st.range query from L to R dot value. This is a long. And then we just do out.println and out.close. Oh yeah. So if L equals null, then return R. If R equals null, return L. Range query. Null pointer exception. What? If L is bigger than rightmost, or R is less than leftmost, return null. So this is returning null somehow. I guess let's first print which query this is. So it'd be helpful if we do this, that way we can see. See what we're doing a bit more. So querying 1 to 4. Okay, so this is leftmost plus rightmost. on in here. Why is so much? Oh, this should be our child. Okay, so some stuff happened. Not the right stuff though. Unfortunate. Okay, so 0 to 4. Yeah, maybe we do something a bit simpler. So let's say n equals 4. And then we have one query, which is, well, let's say the numbers are 1, 2, 3, 4. And then maybe the one query is type 2 from 1 to 4. Type 3. I meant type 2, but this works too. Yeah, okay, so the problem here is that it's not 16. It is n choose 2. So static int n choose 2 int n. This should be n choose 2. And then this should also be n choose 2. And I think this should be n choose 2 as well. Yeah. Both this and this. I think that's it. We can check for multiplies in a minute here. So what is n choose 2? So return n times n plus 1 over 2. Sounds plausible. Do we have any multiplies? No, good. All right, so what does this look like? 6, 4, ooh, we get it wrong. Very nice. Okay, so maybe let's try this. Okay. All right, so what is this third case? So we update, can we just make this just 2 cases? So get it wrong, good. So we update position 4 to a 4. So if we just go like this, and make it 1, what happens? Then we'll probably get it right. We do get it right. So this is the, well, this is kind of the minimal we get. I think we might be able to just do this. So if we make it a 4, or if we make it, I guess, well, this might break it, yeah. So just we do 3 and then query 1 to 4. Still does break, okay. Yeah, so it should be 1, 4, 4, 5. So what is wrong here? So we build our 2 kids and then recalculate for ourselves. Yeah, this is if you're a leaf, you can recalculate. We updated their left kid or a right kid, and then combine them. It seems pretty simple, doesn't it? So this needs a 2 string. This is taking quite a bit of time. Yeah, okay. It's taking like half an hour here. So, a little annoying. But I guess we'll go back to problem D. We should be able to get D in not too much time. So, yeah, shouldn't be the end of the world here. Let's see. Ooh, Neil was quick. Nice and quick, yeah. All right, so for this problem, we need to see what we're doing wrong here. So, recalculating for plus leftmost plus rightmost. And we need here so we recalculate for 0 to 3. So this is wrong, I think, right? I mean, this seems plausible and all, but there shouldn't be a split point there. Oh, wait. Yeah. It should not be 2 to 2. It should be 3 to 3. Okay. So it is only the first step that matters. Yeah, it should just be this step. So recalculating for 0, 1, the first half. Why is that the case? This shouldn't be true. Why is it 1 to 1? That's not right. So what is going on here? So we want to say when it's initially created, what is it? Oh man, come on. So 0, 0, what the heck? Oh, wait, that is fine. Yeah, okay. So where was I before? So recalculating for 0, 1. So the leftmost is uninterrupted, the rightmost is uninterrupted. Gives us 2 to 2. 0, 3 gives us 2 to 2, 4 to 4. So what is wrong with this? What is 4 choose 2? Wait, recalculating for 2, 3. Why? Oh, there should be less than. Ah, I'm a fool. How does this pass data? Wait, is the answer 6 or 10? The answer is 4 times 4 plus 1, 4 times 5 over 2, so it's 20. So why? This isn't right. Okay, 0, 1. So we set this to what? This is so annoying. Set index 1 to true. What? Set index 3 to 4. This is indeed the Z. Be a very good reason to crash. 10, 7, 6, 4. Sounds right. Okay. for the very good samples. I appreciate it. Watch me get roasted for saying that. Looks pretty good. Looks pretty fun. What's our time limit here? We just right on time. 2 seconds. I don't know. Should be fine. I think it is n log n, right? Yeah. A little close. A little uncomfortable, but we should be good. Lots of pretests. Okay. Should be good there. Okay, so how do you do problem D? Expression evaluation error. On the board, yeah, this one. This is kind of annoying. So we want the sum of the leftmost digit to be as large as possible, right? That's greedily doable, I think. So this would be a very easy problem if we didn't have this requirement that every number needed to be at least positive. If the numbers you pick could be 0, the answer would just be the answer in base 10 or base 11. Because there's no way of doing better than that. Yeah. Okay, otherwise, let's say you have some sum. You can put, like, if you have 1, 1, 1, you can distribute the digits like this. But then this thing is too small, so you're gonna have to split it up. I guess, yeah. So you do this, this, and this. So you want to keep this because you get a times 21 bonus for it. You get like an extra bonus for it. So you would probably want to split this up. So 1, 1, 1. So this 100 gets split up into a bunch of tens. How many tens do we know? I guess, yeah, so if we ever have something that isn't a 1, if you have a 2 here, you might as well split the 2 up into 2 1s. Split the 10 up, yeah, so I think this works greedily, yeah. So repeatedly take the smallest thing and then split it up into, so first anything that isn't a power of 10, split it up into powers of the biggest 10 smaller than it, or like sums of the biggest 10 smaller than it. So in this case, this would be like a 7. This would be 70. That's a good example, 172. So this is like a 70, this is like 100. So we make the 100 just be a 100. We make the 70 be 7 tens, and we make the 2 be 2 1s. And then we can assign each of these freely to their own groups. So this will be like, this will be one group, this will be another group, this will be another group. We'll keep doing this. And then we'll give whatever's left over to the last group. But the issue with this is we might run out of groups. Right, so in this case we have 7 plus 1 plus 2, which is 10 groups. but we might need to make like 11 groups, for instance. And in that case, we could do that by taking one of these 10s and turning it into 10 ones. New maths. It's a great song, by the way. Yeah, it's a song about new maths, and the whole song is like, you do a very simple math problem, but you want to do the problem in base 8. So it's a good song. The reason I thought of it is because there's a line in it which is you take the 10, turn the 10 into 10 ones, regroup, and then do something else. And then they do it in base 8, and you get 64s. It's like, where'd the 64s come from? Of course, it's 8 squared, which any programmer would know, but it's funny because it's like, I don't need to explain why it's funny. It's funny. You can take my word on that. As soon as you explain why something's funny, it ceases to become funny. It's like the classic example of a metric ceasing to be a good metric once it's known and being optimized for. Okay, so I haven't really thought about how I'm going to implement this, but I don't think it's that hard now that I know what I'm doing. So we have the sum, and then we have what we're going for here. Let's do that. So int sum equals this, and then int n equals this. So let's make a bunch of buckets. Let's make 10 buckets. Okay, yeah. So then so while sum is not equal to 0, so buckets at 10 pow plus plus equals sum modulo value, and then value times equals 10. Yeah, so we cast to an int here. This should be an int. Over val, so it should be really val times 10. Okay. Yeah, so this will get us how many things we have in each bucket. So while true, I guess, let's calculate the total sum. So sum equals 0, in buckets, sum plus equals I. So we have the sum of how many numbers we can make for free. Do we need this number anymore? I don't think so. So at this point, if sum is bigger than n, bigger than or equal to, then we can do our answer. So we should break. Otherwise, well, the else is implied, because otherwise we wouldn't be here. So yeah, in the other case, we need to find the smallest thing we can split up and split it up. Yeah, so for int mindex equals 1, mindex is less than buckets dot length, mindex plus plus. If buckets at mindex is not equal to 0, then buckets at mindex plus plus or minus minus, and then buckets at mindex minus 1 plus equals 10. So take one of these, make it 10 of the next thing, and then keep going. Okay, awesome. So now we have our answer. And then we can split this up into separate pieces now. So val equals 1, 10 tau equals 0. We'll have these. Yeah, so importantly, we only split something up if we're going to end up using it. So this should end up working here. So for int I equals 0, I guess this is int 10 tau equals 0, 10 tau is less than 10, 10 tau plus plus, and val times equals 10. For int I equals 0, less than buckets 10 tau plus plus, then we'll say parts dot add 10 tau, or parts dot add the value, add this many times. So everything except, well, the first n minus 1 things we just print out on their own, and the last one we print out several times. So for these things, we want to print this out on their own. So sys out parts at I minus 1. And int sum equals 0. That should be fine, I guess. So int I equals n. Yeah. I is less than parts dot length, and parts dot size, plus. Sum plus equals parts dot get I. So that's sum. Well, I guess we could just say sum divided by equals 10 here, and then here we would say sum mod 10. $195 do not, in fact, add up to the right number. What do I have here? This should not be n. This should be n minus 1. 197, 96. I think that should be fine, yeah. 17. Yeah, that's fine. Because these add up to not the right number. Oh, I guess it's fine. Yeah, because everything is in the ones column anyway, so we should be good. Okay, then 1090, and then a bunch of 1s and 2, and then I think this doesn't matter. Yeah, I don't think that matters. That should be fine. I guess let's see. What does Codeforces tell us? I think it's unlikely we get test 1 right and then another test wrong. Way to call my bluff, Codeforces. It's unlikely we get a test other than test 1 wrong. Immediately gets test 2 wrong. Okay. So, yeah, what could be the issue here? Yeah, this is interesting. Okay. Why? So what am I doing wrong here? So we have some buckets. We have some buckets for value. They're 10 pow. Well, sum is not equal to 0. What is val? So I go to the next bucket. Sum mod 10, divide out 10. Okay. So we want the sum of digits in the bucket. If the sum of digits is at least n, then we break. Yeah, that's fine. Why is this wrong? I think this should be right. I'm missing some case, surely. There are lots of wrong submits to this. There are a few. I don't see why not, to be fair. Okay, let's try reading this maybe. Alice has an empty grid with n rows and m columns. Some cells are marked and no marked cells are adjacent to the edge of the grid. Okay. Alice wants to fill each cell with a number such that the following statements are true. Every unmarked cell is either a 1 or a 4. Every marked cell contains the sum of numbers in all unmarked cells adjacent to it. Every marked cell contains the sum of numbers in all cells adjacent to it. Okay. Every marked cell contains a multiple of 5. Are cells adjacent to it? Yeah. So these two here and here are 1 plus 4. Okay. Yeah. Is that 5? In unmarked cells adjacent to it. Okay. So you need to have the same number of 4s and 1s. Either one, yeah, you can't ever have 3 things adjacent to you. Right, that's impossible. So you always need, well, if you have 4, it's pretty easy, but if you have 2, you just have an edge between them, meaning these 2 things have to be different, and then you should color the graph at the end. Shouldn't be that bad, actually. We can probably do this. Yeah, so is there any weird cases here? I don't think so, right? So you just, yeah. So either you need, I guess you might have a little bit of a weird case where if you have something like this, okay, so let's say we have, let's do x's because it's easier. We have an x here, dot, dot, this sort of thing. Oh, wait. Yeah, that's cool. Oh, neat, neat. So, since no x's are on the grid, that means this contains a loop. This is like one giant loop. Which means what does this tell us? Makes it easier, doesn't it? It means the grid is split up into inside and outside. Yeah, so these would be, if you do a chess coloring, these would be the same. Yeah, that's cool. That's really cool. So the grid, yeah, so this needs to be a loop. You need to make loops like this. And then every time you do this, this would be distance 1, this would be distance 2. Every time you do this, you invert what it looks like. So that way this would be an O. And then you sweep through again and solve all the x's. That should work as long as nothing has odd degree. Yeah, so this is just a BFS. So this is an easy problem. I guess it's easier to solve F than it is to figure out D, figure out what our bug is with D. So let's do that. This is a cool problem, actually. I really like it. So we have the height and then the width. Yeah, okay. And single test case. Okay. Right, so then we need int array distance, new int array width by height. So array deck integer x's array deck. Let's just make sure this works here. So we have this. And we have distance 1, 2, 3, 4. Yeah. Okay. Okay. we have that, and then we have, I guess we can just do this. So we can say list with -1, and then x's dot add 0, y's dot add 0, dist to 0, 0, 0. Well, not x's dot is empty. Int start x equals x's dot remove first. Int start y equals y's dot remove first. For int b equals 0. D is less than 4 plus plus. Oh, we first need to check if there are any illegal squares. So if so if nx greater than or equal to 0 and ny is greater than or equal to 0 and nx is less than or equal to width and ny is less than or equal to height, less than, and grid at nx ny is equal to dot, then count plus plus. So, oh wait, we also need, does it matter? Yeah, we need to be an x. And grid at nx, or at xy equals x, capital X. Hope it's capital X, looks like capital X, okay. So if this is the case, then increment us. If it's odd, then it's impossible. Otherwise it is possible. Okay, and the end, yeah, so then we need int array answer to int array width by height. How much time do I have? It's gonna be close. So yeah, so if grid xy equals an x, then continue. And then ny is y plus dyd. And then we say grid at x, or I guess this is ants at xy plus equals ants at nx and y. We only want to do this if grid at nx and y is equal to a dot. Yep, and then for y equals 0, less than height, y plus plus. Six out, and then for x equals 0, less than width, x plus plus, 6 out. Grid at xy, sorry, ants xy. Okay, we need to figure out this part now. So how do we, what do we do for the answer if it's a period? So int default equals, I guess int normal equals x plus y mod 2. This thing, whatever this is, times 4 plus 1. What's wrong with this? Oh, I'm missing a parenthesis. Well, okay. So if dist at xy over 2 mod 2 equals 0, then ants at xy equals normal. Otherwise, ants at, oh, it's either, so this should be times 3. It's either a 1 or a 4, right? Yeah. So otherwise, ants at xy equals normal equals 4. If it does, make it a 1, otherwise make it a 4. Okay, so now we just need a BFS and we should be fine. We can write a BFS in 15 minutes. So this is this. Okay, so we need int n x equals sx plus dx at d. Then ny equals sy plus dy at d. If nx less than 0, or ny is less than 0, or nx greater than or equal to width, or ny is greater than or equal to height, and then continue. If dist at nx, okay, so yeah, okay. So we want to say yeah, we can process everything a second time, that's fine. But we just want to say so int nd would be grid at nx and y equals a period. If it is, make this the start distance. Otherwise, it would be start distance plus 1. So we have the distance to this new space. So if dist at nx and y equals -1, or dist at nx and y equals is greater than start distance, new distance, then add it to the queue. So dist at nx and y equals new distance. And then if SD equals ND, do one thing, otherwise do something else. So here we say x's dot add first and x, y's dot add first and y, otherwise we add the end. 0, 1 BFS. This isn't right. Shoot. Fundamental solution flaw. Fundamental solution flaw indeed. Shoot. Shoot. These need to be different, these need to be different, these need to be different. Darn it. Man, that was so cool too. So, does this work? So this will handle any corner just fine. And across an edge, things are the same. So what if we make this just the Y? Oh. Dist. Let's, I guess, just submit here. Alright, let's pretest 5. 1, 2, 3, 4. Oh man. For real? That's so annoying. Is it my BFS? What if we have something like this? Well, we still have an Euler tour here. This should be right. In theory, I think this works. Oh, I guess all of these are the same height. That's annoying. What about 2, 3? So I guess we're just looking for data here. 114. What? Oh. So it could be this. If it isn't this, what else could go wrong? We could be printing... Runtime error test 5. Okay, so... what would that mean? That means... well, if it's... it can't be 4, because then they'd all be connected. So they'd all be the same. They'd all be in the same group. Oh, they can't... they might be disconnected. Yeah, if we have something like this. We could have this here, and then we could have... so these three are connected, or this one's disconnected. So in this BFS, yeah, I think it's less than 8. Why are we crashing? Eight. These get connected somehow? Oh. Oh, okay. So, yeah, we kind of only want this. We only want this if if they're both periods, I guess. Create it, and x and y is not equal to a period. Continue. This is not a legit solution at all. I think maybe just the BFS is the easier way of doing it. That's sketchy. I don't know about that, man. That's very likely to fail system tests. How many pretests were there? Hmm. Yeah, I don't know how I feel about that one. Okay, what are we getting wrong for problem D? Who knows at this point? Who knows? Yeah, I don't know. I don't know why this would be wrong. I'm kind of interested in the case. I don't know that I'll be able to see it though. Rainboy, nice job, sir. Nice job. Strong performance today, as usual. Well done. Okay. Yeah, so unable to get D. Some kind of silly issues, I think. That's fine. Is this Daruha? This is the guy who invented is Daniel Slater, inventor of link cut trees. Look at that. Glad to see him participating. That's always fun. Cool guy. Made some very powerful contributions, at least. Okay. There's the contest. There we go. Okay. All right. I guess solution time. So we'll talk about solutions to everything. My solution to D is apparently slightly wrong, or at least my implementation has issues. But other than that, I thought it was a very good contest. I really enjoyed the problems. I thought the problems were absolutely terrific. F was great, although I don't know why my first submit was wrong, but it was great. I don't know if my second submit's even right, but it's a cool problem for sure. E was a little classical, but still good. D was interesting. And then A, B, and C I liked. Okay, let's talk about them. Oops. So for problem A, domino disaster, you have this grid, and you're given one of the two rows of the grid, and each row is something like this. So you have a 2 by n grid. So there's some dominoes in it that tile the grid, so maybe they look like this. And you're given one of the rows of the grid, maybe this top row. You want to print what the other row is. For each domino, you're given whether it's like the left side or the right side, or here this is the up side or the down side. So you're given one of those for each domino, and you want to figure out what the other grid is. So the key observation here is that for one of the rows, like if you look at the top row, anytime you have a domino that's 2 across, the only way of matching it is another domino that's 2 across. If you have a domino that's 2 across and it's offset like this, then you're always going to have this hole on one of the sides, and you can fill it in with another 2 across one, but then you'll have a hole in the top. So you need, like, each group of, like, the first 2 dominoes, it either needs to be these 2, or it's got to be this, and then either like 2 like this, or it's got to be this, and then 2 like this, and so on. So basically, all you have to do is take the up and down dominoes and flip them. And my implementation of this was good enough, I guess. It looked like this. So I read in the length, I just skipped that part, and then I replaced all U's with X's, basically just to get rid of them. Then I replaced all D's with U's, and then I replaced all X's, which were the initial U's, with D's. So I flipped the U's and the D's, and the left and right stay the same. So yeah, it's a pretty simple problem. Understanding that this is the only way of doing it is the important part. And then once you have that under your belt, it shouldn't be too bad, I think. So yeah, that's problem A. Pretty easy, pretty easy. MEX or mix-up. So yeah, this problem talks about the MEX, which is the minimum excludent. It's very important in game theory, so it's something I'm very familiar with, and probably most people who are pretty good at competitive programming are familiar with the MEX. But if you're new to it, it might be something that's a bit scary seeming. But basically, in a set of numbers, it's just, all it is the smallest thing that isn't in that set. So we'll do a quick example here if you're new to it. If we have the set of numbers 3, 1, 4, 0, 6, then you'll notice if we look at these, oh, maybe we'll have another 0 in here. If you look at these numbers, the smallest thing that isn't in here is 2. So there's no 2, so the max of this set is 2. There can be things bigger than 2 in the set, and there can be duplicates of things smaller, but there's no 2, so 2 is the max. And then XOR, you should know, but basically if you write each of the numbers in base 2, so we'll write it like this, so we'll write 3 is 0, 0, 1, 1, 1 is 0, 0, 0, 1, 4 is 0, 1, 0, 0, 0 is obviously 4 zeros, and then 6 is 1, 1, nope, it's 0, 1, 1, 0. So I guess we don't need this first column because it's all zeros. But for the rest of these, we just care, does each bit occur an even number of times or an odd number of times? So in this case, actually every bit occurs an even number of times, which means they're all, which means the XOR of all of these numbers is 0. But we could, in theory, like get rid of, that's not right. The XOR should be, oh yeah, it is 0. So we get rid of the 6 here, and I also get rid of the 0. So if you get rid of, oh, I got rid of one of the zeros. There's another 0. So if you get rid of the 6, then here are 4 numbers, and then in this case, the XOR would be, well, the first number occurs an odd number of times. So this is going to be a 1. This occurs an odd number of times. This is an even number of times. So in this case, the MEX, or the XOR is 6. Now you'll notice the number we removed was 6, and that isn't a coincidence. If you have a group of numbers that have an XOR equal to 0, and then you remove one of the numbers, the XOR that's going to be left is equal to the number you removed. And that's because you've just changed the parity of the number of bits for every number in that number's binary representation. So 6 is 1, 1, 0. Before everything was even, and now we've just changed this bit and this bit. So now since everything was even, these 2 bits got changed. That means the XOR is going to be 6. Yeah, so that's one important property of XOR. And for this problem, we can notice that the XOR, you can basically make it whatever you want with one number. So if the XOR is 7 and we want the XOR to be 3, we can change the XOR from 7 to 3 with just one number. So in this example, 7 is this and 3 is this. So if we want to change from 7 to 3, we want this bit to change here. So we just want to XOR it with this number, which is 4 in binary. So we can change it however we want. There are a couple cases for this problem though. So we want we want to choose the smallest possible set where the MEX is A and the XOR is B, and we want the length of the shortest possible set. So okay, the first observation is, let's say the XOR, or let's say the MEX is equal to 5. That means the size has to be at least, well, it has to be at least size 5, right? Because it has to include numbers 0, 1, 2, 3, and 4. If it doesn't include these numbers, the MEX won't be 5. Now, the XOR of these numbers is going to be 4. I just did that in my head, but you can do it on paper to verify if you need some XOR practice. The XOR of these numbers is 4. So if the XOR we're looking for is also 4, that means we don't need to add any additional numbers. So the answer will be 5. If the XOR is some other random number, right? Maybe the XOR is like, I don't know, 0. Then, okay, we have these numbers. We can add another 4, and then the XOR will be 0. So in that case, we can make the answer be 6. We can add one more number. And we can almost always have an answer of n plus 1. There's one time we can't, though, and that would be if the number we needed to add here was a 5. Because if that's the case, then we've just broken our MEX. So we have to watch out for that. That's in the first sample. It's very nice. But yeah, we have to watch out for this case. And it's pretty easy to handle. We just say like, okay, well, if the max that we're looking for is equal to the XOR of the prefix, then we want to be careful there. Okay, so just to elaborate on how you actually solve this, there's one more part of the problem, which is you've got a bunch of test cases, and you have to handle those quickly. So to handle these things quickly, what you want to do, I guess maybe they make some guarantee. No, they don't. They just, because you're printing the size. So, okay. So to handle these test cases quickly, what you can notice is this XOR part that you're interested in, it's always the XOR of 0, 1, 2, 3, 4, 5, 6, all the way up to some number n. So we can pre-compute this for every prefix of 1 to like a million, right? So the XOR of the first one of just 0 is just itself, and the XOR of this is just this. And then for 2, we'll look at the XOR of the previous thing, XORed with 2. So we can figure out all of these things, store them all in an array. We can do that in linear time. And then we can check each of the 3 possible cases for all of the future numbers. Yeah, so that's the idea for problem B. Okay, for problem C, carrying conundrum. So Alice just learned addition, but she doesn't carry right. She carries across 2 decimal places rather than just 1. So I'm sure there are lots of ways. So the question is like, you're given some possible sum that she wants to reach, and you want to know how many pairs of inputs could reach this sum where both of the inputs are positive. So yeah, I'm sure there are a bunch of ways of solving this problem, but here's the way that I used. So you're going to have some sets of numbers here. So you'll have like two groups, for instance. Some 4-digit number, some other 4-digit number. We might have leading zeros, those are allowed, but we'll just say we've got these 2 numbers here. And these circles aren't zeros, they're just placeholder digits. If we're going to add these, when we do, let's say these 2 overflow. So in that case, we'll put a 1 here because we're going to have a carry bit in this position. And then maybe these don't overflow, so we have a 0 here, and these do overflow, so we have a 1 here, and then these overflow, so we have a 1 here. So we have these 4 numbers. They might do a bunch of stuff. They'll influence all of these 4 positions, and then they also create these 4 carry bits. Well, the key thing to notice here is if we're looking at these 2 numbers, the only thing that the rest of this number cares about regarding these 2 numbers is what this carry bit here is, and also what this sum is. So we need to make sure this sum is correct, and then if this carry bit is correct, none of the other numbers care about what these 2 numbers are. So we can like brute force all of the possibilities or whatever, and then we'll be fine with these 2 numbers if we can satisfy them. And we want to make sure that the carry bit is satisfied and also this bottom bit is satisfied. So since the only reason the other numbers would care about this pair at all is because of this carry bit, we can brute force all of the possible ways these carry bits might happen. And since the number is 10 digits long, and each of these have 2 possibilities, there are 2 to the 10-ish possible carry methods, right? Possible ways of having the carry bits get passed around. So we can brute force each of those possibilities. So we're going to brute force each of whatever these carry bits are. And let's say we know them. Well, then for this pair here, it's pretty easy to calculate what it should be, because we know, okay, let's do a more concrete example here, so it's a little bit fewer symbols. So let's say this is a 6, and then we have a 0 carry bit. That means these 2 numbers have to add up to exactly 6, and they can't add up to 16. It's got to be exactly 6. So we can just say, okay, well, of all of the possible numbers, how many pairs are there where a plus b add up to 6? And you've got, well, you have 6 plus 0, you have 5 plus 1, and so on. And you can math this out in constant time if you want to, or you can just pre-compute it because there are only 100 pairs of 2-digit numbers that you can add up, and you can pre-compute where each of them go. Or, I mean, you probably don't even need to pre-compute it because the runtime is not going to be that tight for this problem. Don't quote me on that, but you probably don't need it. So, yeah, that's the idea. We brute force what this carry mask is, and then we know for each digit we can, or for each like power of 10, we can say, okay, what should this be? If it should be this, we check, is it possible? And if so, how many ways are there of doing it? The only thing that winds up being like impossible, for instance, is if on these two digits here, you wind up with a 1 here, but you want a target sum of 0. So in that case, it's impossible, and you have to say there are 0 ways of doing that. I forgot to show my code for B. Here's what it looks like. We'll take the XOR prefix, and then for every pair of numbers, and then here we case out these 3 ways. But for C, here's what the code looks like. So it's a little bit more messy, but first we calculate for every number from 0 to 18, really to 20, how many ways are there to add up 2 single-digit numbers and get that number. And then for the rest of this, we say, okay, we're going to store these bits as the input, but then we'll store it. So index 0 is 10 to the 0 power, index 1 is 10 to the 1 power, and so on. Because I think that makes it easier for me to think about anyway. And then we'll brute force this end mask. So this is the mask of which bits get carried. And I make sure the first 2 bits are both zeros. So really this only has 10 interesting digits. You can speed it up a bit. Mine's about 4 times slower than it needs to be, but that's fine because we have plenty of time for this problem. So then I'll look through each of the positions and I'll say it's impossible if the target sum is negative, right? So, but the target sum is what we want these 2 numbers to add up to. If we have a carry bit that's being added to this position, then we need to have one smaller of a sum. So if the number we want at the bottom is maybe a 5, and then we have a carry bit, that means like some previous digit added to us, we really only want these 2 numbers to add up to 4 rather than 5. Otherwise we want them to add up to 5. And then also, if we need to overflow in this position so that we create a carry bit for someone 2 steps down the line, then we need our sum to be 10 bigger. So yeah, so like if let's say we did have a carry bit, so we wanted our sum to be 4, but we also have to overflow here, then we really want our sum to be 14 rather than 4. And then you say if the target sum has to be negative, obviously there are no ways of doing that, but otherwise you just multiply by the number of ways to satisfy this digit. And then that's your answer. You have to subtract 2 at the end because you can always do like n plus 0 or 0 plus n. Those are always possible, but they want all the numbers to be positive. So I've just counted those 2 ways in the beginning, but you can just subtract them out at the end because they're always going to be possible. And then n is always, well, yeah, n's always at least 2. So you don't have to worry about it being 0. Awesome. Okay, I hope I didn't fail system tests. Yeah, looks good. Sounds plausible. Let's move on to problem D. So D, I have an idea for, but apparently it's wrong. The problem is you have a bunch of integers in base 10 that add up to s. And then you want them in base 11 to add up to the biggest number possible. So yeah, here's the observation here. So we can split up each digit. Like, so let's say we have some numbers here. Let's say we have like numbers 1, 7, 1, 7, 2, and then 2, 5, 6, for instance. Let's say just like 25. Say we have these 2 numbers. So all that matters is like the sum in this column, the sum in this column, and the sum in this column. Because in decimal, we need this times 100 plus this times 10 plus this times 1. We need this to equal whatever our initial sum is, the sum of all of the numbers initially. But then in base 11, we need this times like 121, which is like times 11 squared, plus this times 11, plus this times 1 to be as big as possible. So yeah, we can abuse this by saying like, okay, we really want the bigger numbers to be as big as possible because we get a much larger bonus per number for each one of those. than the smaller numbers. And also, like ideally, we want everything to be like kept as far left as possible, which is what would happen if we could just make all of the numbers except 1 be 0. So the first number would just be the sum in decimal, and the rest would just be all 0. And that's, I'm pretty sure, the best answer you can get. Unfortunately, you can't do that. So sometimes you have to take from the biggest number and give to other numbers so that your sum stays as close as possible to whatever you're going for. So what can we do to change our sum in the simplest way so that it doesn't really decrease that much and stays closest to the answer? So there are a couple things here. Let's look at the number like 123, for instance. So the first thing you can notice is you can take this 3 and you can just separate it. So you can have 120 and then this 3. And you've added support for having another number here, another positive number. And you haven't changed the column-wise sum for each column. So you're fine doing that. You can also make this 3, in addition to just being a 3, you can make it be like a 1 and then a 1 and a 1. So now we've created support for some more columns here by doing this. And then same thing with this 2. We can separate the 2 out, so we can get rid of this 2. We can make it a 0 here. And then we can make it a 10 here and then a 10 here. So 123 can actually support a total of 2, 3, 4, 5 different numbers. Or 6 different numbers, excuse me, because the sum of its digits is 6. So with just 123, without decreasing the sum in base 11 at all, we can support 6 numbers, because the sum of digits in base 10 is 6. Now we can support more numbers. We can support up to 123 numbers. However, doing this is maybe a bit annoying. So what we're going to have to do, let's say instead of 6, we want to support 7 people. Well, what we can do is we can take this 10 here and we can turn it into 10 ones. So if we have to, we will do that, and then we have 10 ones, and we can continue going from there. And then at the end, we'll have this list of numbers, so maybe we'll have like a bunch of 1s, and then some 10s, and then we'll have maybe a couple of 100s. And what we can do is we can say, okay, like make this its own number, make this its own number, make this its own number, and then combine the rest of these all into the same number. And I'm pretty sure this is a legitimate thing you can do, because you'll only split up a number if you didn't have enough numbers initially, which means those numbers will all get used by separate pieces. And since you've created an additional 9 numbers, you won't overflow an entire digit in your answer, because all of those previous digits will have been accounted for. Maybe it's possible that doesn't work. No, that should work. I think it works. I think that always works. Yeah, that should always be fine. So I don't know why my solution is wrong. So I might be leading you guys in the wrong direction here. But I think that's a legit way of doing it. To summarize, you split all of the digits up because we're just looking at this by column, right? So we look at each power, like each digit separately. And we just want these digits to be split up into as many numbers as possible, and then we combine them into exactly n at the end. And then if we don't have enough of some digit, then we start with the tens place and we push those into ones. And then if we still don't have enough, we take the hundreds, we push them into tens. And then if we still don't have enough, we take the tens, we push them into ones some more, and then we go to the thousands, into hundreds, and then we repeatedly find the smallest digit we can shrink it by 1, and then increase the next one by 10. So yeah, I guess I won't really show my code for this because it's wrong, but I guess you can, if you're really interested, you can pause and take a look here. But I'm not sure. I'll have to debug this after. All right, problem E, non-decreasing dilemma. So this is a very simple, easy to explain problem. You have an array, and then you have 2 types of queries. One is change this element to some other element, and one is count how many sorted subarrays exist in this array. So yeah, and basically we don't want we're not interested in how many distinct arrays there are, just how many distinct positions there are where it's sorted. And each of those ranges are continuous. So how do we do this? So the important thing here is most of the information of the array isn't important. All we really care about for this array is if it looks like, let's say the array looks like this. I'll just draw the things from left to right where this is their value, this is their index. So maybe the array looks like this, possibly. The important thing here is here you have a decrease, and then here you have a decrease, which means these two positions split the array up. So anything in these 4 elements, you can choose any continuous range. Anything in these, you can choose a continuous range, and then anything in these, you can choose a continuous range. So this is a much easier structure to deal with than just having lots more information about what the values of each of the numbers are, because we don't really care. We just care about whether they're split points or not. The other thing is, this doesn't change very much in a particular query. So if we change some value, the only thing is, if we change the height of one of these blue dots, the only thing that can happen is the thing to its left might create or destroy a cut point, voice crack, and the thing to its right might also create or destroy a cut point. So there are only, if you change some element, there are only 2 positions that might change. Everything else is going to be constant. Which is really nice, because that means we can just do a segment tree, ignore this initial problem, and solve the secondary problem of okay, please maintain these cut points, and then do some aggregate on what the cut points look like overall. So yeah, let's look at the second problem for now. Hopefully this conversion to a simpler problem made sense to you. Let's look at the second problem. So the problem this turns into is okay, we have a bunch of elements here. And now we have this segment tree, which we're going to use. And we have to maintain, okay, we have to be able to add a cut point. We have to be able to remove a cut point like this, to erase one. And then we have to say, how many continuous ranges are there, like this, where both ends of the range are inside the same segment and not intersected by any cut points. So yeah, in this case, you have 6 choose 2, or is it 7 choose 2? It's either 6 choose 2 or 7 choose 2. I guess it's 7 choose 2. But basically, it's 6 times 6 plus 1 over 2. That's what this comes from. Yeah, so the question is how many of these are there? And we can maintain that with a segment tree. So we use the same trick that I taught in my my tree, or I guess I taught it in one of the segment tree algorithms thread videos. But yeah, it's a solution to Sneetches. So in Sneetches, what you store is for each range, what we want to maintain is some interesting part about the inside of this range, and then also something about the prefix and the suffix of this range. In this case, we want to store how many unbroken zeros are in the prefix, and then how many unbroken zeros are in the suffix. Then when we want to combine 2 ranges, well, we have the prefix information here, we have the suffix information here, we have enough to combine them here about the inside, and then we also have everything about the middles of both of these here. So the middle will turn into just this part here. And that's all we need to do, right? So if we have the information about the middle, the stuff after the first cut and then before the last cut in some range, we have all of this information stored. And we have the stuff about what happens here and what happens here, like where these first and last cuts are, then we can calculate the information for this range that we care about very quickly. Yeah, so what does that look like? Well, the main method here is quite boring. We just have a segment tree. We store whether or not there will be inversions at each position, and then our answer is just this range query. So everything interesting is happening inside the segment tree. And the segment tree actually is also pretty boring. It just stores this data object, and everything is just like, well, we just need this combine method to combine the left kid's data with the right kid's data. Propagate your updates to whichever kid cares about them, and then answer the 2 queries and combine them for the answer to a range query. So the question is really just how do we combine these datas? If we have some data on the left and some data on the right, what do? Well, if one of them is null, just return the other one. That makes the other stuff easier to handle. The size of the new data is going to be really easy. It's just the sum of the sizes of the previous two. And then this new L is like the new L prefix and the new R prefix. You got to be a bit careful here because it's possible there are no split points in the left range that we're considering. So if that's the case, if there are no split points in the left, that means that the new middle sum will be like okay, so what does this look like? We have some continuous range here. It's all like just things without split points, and then we have some split point over here. We might have some stuff on the right side. We might have some stuff. So this is like the right kid. So here, the new left prefix will be this part. Right prefix will be this, and the middle sum will be the right middle sum. So this is the new middle sum, and then the new left prefix will be the left thing's size plus the right thing's left prefix. Otherwise there's a cut point here, so the left prefix is easy to figure out. And then we have the same thing, but on the right side, just kind of mirrored. And then finally, if we haven't set the new middle prefix yet, what this means is we have a split point on the left, a split point on the right, which means there's going to be some suffix of the left and prefix of the right that contain one continuous range, which now is blocked off. So we need like n-choose-2 stuff on this, as well as other middle stuff here, as well as other middle stuff here. And this will be the new data. So yeah, this is how you combine it for problem E, and that's the solution. Okay, the last problem is problem F. Did I fail it? I'm in Q still. Okay, this is a little sketchy. Little sketchy. So yeah, I don't have a total proof for why this is right, but I can get close. The idea is this. So we have this 2D grid, and there's this really nice property about the grid. There are a couple of properties about it, actually, where we can ignore most grids. Let's look at this grid here. This is a bit messy, but okay, that's fine. Yeah, so yeah, I guess this is what's important, I think. Yeah. This is not perfectly drawn, but you get the idea. So we have this grid of x's and dots, and we want to replace each dot with either a 1 or a 4, and replace each x with a multiple of 5 equal to the sum of all dots around it. So what we could do is we could place this with a 1, this with a 4, and this with a 5, for instance, and that would work for this x here, because everything else around it is an x, so it won't contribute. Yeah, so a couple observations here that should be pretty obvious. The first is that if we have an x, we need the same number of 1s as 4s around it. If it has 1 1, it needs 1 4. If it has 2 1s, it needs 2 4s. If it has 3 1s, we're in trouble because whether the last thing is a 1 or a 4, well, 3 1s on its own obviously doesn't work. If the last thing is either a 1 or a 4, it's either going to equal 4 or equal 7. Neither of those are a multiple of 5. So you need the same number of 1s and 4s. Also, I should say, you can't ever have one thing or 3 things, right? So if you have one thing, the sum's either 1 or 4. If you have 3 things, you can do it out by hand, but it should be pretty clear that the sum is never going to be 5 or 10 or 15 or 0. Because if each of the things you're adding are 1 or 4, it's just not going to work. So yeah, that's the idea. So each x needs the same, we're going to rephrase the problem, is it needs the same number of 1s and 4s next to it. That's easier to think about, in my opinion. And then where do we go from there? Well, so the first observation from that is that every x has even degree. Because there are no x's on the boundary, every x, it's got to have degree 2 or degree 4. So yeah, in this case, every x has degree 2, but it's possible every x has degree 4. Or not every x, it's possible most of the x's have degree 4. You're still going to need some x's with degree 2, right? You're still going to need some corners. There are going to be corners. But you might have a bunch of interior x's as well. Yeah. But you're still going to need a lot of x's with degree 2. Okay, so the next thing is that you're also always going to have an Euler tour on this. So what is an Euler tour? Well, you've got like some path that passes through all the x's. And it might be disjoint paths. Like you might have one path like this and then another path out like this here. But you can pass through each x exactly once in some path. And you can make these shapes here, and they might be nested. You might have some path inside. But this is always going to be possible because each of the x's have an even degree. So that's kind of cool. It's a fun fact. I don't know if it's useful or not. Turns out that it might be, depending on whether my solution is right. But yeah, it's interesting for sure. So how do we use this? Well, we can actually come up with this just genius construction idea here, which is there are kind of two types of items here. I guess they're like a couple possibilities. One possibility for an x is that it's surrounded on all four sides by other x's. So in this case, it doesn't really matter what we do because the sum of this x is going to be 0 anyway. Let's say it isn't surrounded by all four. Then there are two, like kind of two possibilities. Either it looks like this. So here we're focused on this x. Either it looks like this. There's an x above it and below it, but not to its left or its right. Or you can have like the same thing sideways, or it's going to be a corner, these are kind of different. So in this case, the key observation here is that if this is like inside of some loop, then this will be outside. So we'll switch whether we're on the inside or not when we go across this x. And for this corner, well, we don't switch whether we're on the inside or not, but we do switch the parity of the y, right? So the parity of the y changes. You could also say parity of the x, but I say parity of the y. So the parity of the y of these two elements is different. So in other words, what we want is we want the parity of the y to change only when you stay on the outside. So if these two are connected, you want the parity of the y to change. If you go from the inside to the outside, the parity of the y is going to stay the same, but you want these to be different, right? You need one of these to be a 1, one to be a 4. So what we can do is we can say, okay, we're going to draw this line like this all the way across like that. And then here we're not going to draw a line, but if we like enter some shape, then we'll change whether or not we're drawing the line. So we won't draw a line for this. Here we will draw a line, but now we're on the inside, so we don't want to stop drawing the line, and then we'll continue drawing it outside. Here we'll stop drawing the line. Okay, now we're inside, so we start drawing, and then outside we stop. And then this is the next row, so we stop here, and then we start here. Then we stop, we start, and then we stop. And then we do this again, and then we do that. So it turns out this solution just works where everything I colored in blue is a 1 and everything else is a 4. And it's a super neat solution. It relies on this sort of principle here. And I think it's really clever. I feel super clever having come up with it. So this makes me really like the problem. This is the kind of thing where it's like, it's constructive. It has this interesting observation here. It's cool. And it's like simple enough that it's understandable, kind of. But yeah, like it works, and also you get it the last minute of contest, so it just feels great. Okay, let's see. I guess let's end this video seeing whether or not I got the problem. I feel like that would be a cool ending. But yeah, I guess nice job to Monogon for beating me. Good job. And for Neil. Neil's also doing solution videos, so yeah, tune into his stream, I guess, if you'd like. If it's still going on by the time this gets processed. I do want to see whether this is ended or whether this is correct or not. But it might be a few minutes here. I guess we can probably see the queue. Oh, they're all running. It looks like. Okay, so we're at 150. 151. So when was my submission? 152. My submission was 158. So we have a bit. 152.40. 153. It's gonna be a minute. Yeah, I feel like at this point I've already committed, you know? And plus you guys have the ability to skip forward in the video. So yeah, there you go. I guess does this look really foggy? Is this foggy? Is it out of focus? I don't know, maybe not. $155. Progress is being made. Got a new haircut. I feel like my haircut's kind of a little too short, maybe. Anyway, it'll grow back. Great part about being a guy. Okay, 98%. Almost there. 157. Here we go. We got one more minute. 157. You just gotta sit back and appreciate the immense amount of computing power going through Codeforces servers right here. Okay. My submissions. Here we go. Did we get this? Usually I wouldn't sit here and watch, but this is just so on the edge of like, well, it might be right, it might be wrong. I did not prove any difference between these submissions. Was like legit. So, very sketchy. Test case 17. 20. 22. 25. Looking good, looking good. The tutorial's out already. Nicely done. There we go, we got it. All right, very cool. So that was a legit solution explanation then. Hope you enjoyed. I wonder if that was what was in the tutorial. What do we think? Oh, they've got video solutions. Okay, nice job. Yeah, it sounds maybe similar. I'm not sure. Yeah, okay. Anyway, cool. So yeah, I guess that's all for me. Thank you for watching. I realize that I might be getting beat out here by video solutions from Neil and from the editorial, but I don't know. If you enjoy my explanations, hopefully these are still helpful. So yeah, that's all. I hope you have a great day. Hope you did well in your contest, and I'll see you in the next one. Goodbye.